All right, so our next step in working with chemical equations, other than just writing them out and balancing them, is to determine what type of reactions there are. And chemical reactions can be very easily classified based on how the atoms are rearranged on the product side from the reactant side. And there are 5 different ways that we typically classify chemical reactions. We classify them as either combination, decomposition, displacement, exchange, or combustion. And the way we go through and identify these different types of reactions is based off of the nature of the reactants and the nature of the products that are produced from the reaction. In some instances, we'll start off with 2 reactants, they become 1, or 1 reactant becomes 2, or there's a displacement of an atom or an exchange of atoms. We'll go through each one of these individually and discuss how we can identify them, and then eventually how we can actually predict the products of those chemical reactions. So the first type of chemical reaction I want to discuss is what is known as a combination reaction. This is a chemical reaction in which a single product is formed from 2 or more separate independent reactants. And so we have a myriad of examples that are here. These can be elements or compounds, but again, the easiest way to determine whether I have a combination reaction or not, and sometimes this is referred to as synthesis, just an FYI, is that I start off with 2 reactants and I get 1 product at the end. So at the very beginning there, I have hydrogen and nitrogen, it becomes ammonia. We start with 2 reactants, it becomes 1 product. Magnesium oxide and carbon dioxide are both compounds, but they still form 1 product, so as a result it is a synthesis or combination reaction. Same with CO and oxygen, and Na and Cl, they're all combination reactions because 2 reactants form a single product on the right side of the equation. The opposite of that is what is known as a decomposition reaction. This is a chemical reaction in which a single reactant is converted to 2 or more products. So essentially it's the reverse of a combination. We start with 1 reactant and we end up with 2 products as a result of that chemical reaction. So they can be elements or compounds. Looking at the first example there, we have iron hydroxide, and that decomposes into iron oxide and water. Water itself decomposes into hydrogen and oxygen. Silver bromide can decompose into silver and bromine, carbonic acid into carbon dioxide and water. Again, the nature of this is that 1 reactant ends up becoming 2 products on the product side of your equation. A displacement reaction. This is a chemical reaction in which an atom or group of atoms displaces an atom or group of atoms from a compound. So notice here that this specific reaction starts off with an element plus a compound, and we get that on our product side. But what ends up happening is that the individual element that is on the left side ends up replacing one of the elements in the second compound in the chemical formula. So for example, in the very first one there, potassium reacts with water. Well, potassium is replacing one of the hydrogens in water to create potassium hydroxide and oxygen gas. Second one there, magnesium. The magnesium replaces the copper. The third one, the zinc replaces the hydrogen. And then the last one, the chlorine replaces the iodine. So you can see here there's a variety of different ways that we can have exchange of chemicals. But the big thing to keep in mind here is that it is more than likely going to be just an element plus a compound, and we get an element and compound as a product. One of the elements has essentially switched places with what you find in the compound. Now, how do we know what gets replaced? Well, a fairly easy way to remember this is that metals will displace metals, that is, they'll trade places, or nonmetals will displace nonmetals. Another way to look at it is that things that are positively charged will displace things that are positively charged, and things that would normally take a negative charge will displace things that are negatively charged. Look at the example of magnesium and copper. They trade places in that second equation, and that is because magnesium is a metal and copper is a metal. They both have positive charges. They're not going to bind together, but rather they're going to switch places. Same with zinc and hydrogen here. Even though hydrogen is a nonmetal, it has a positive charge. Zinc in its ion form typically forms a positive charge, so they will switch places, resulting in zinc chloride and hydrogen. Chlorine, however, is a nonmetal, and so notice that when it reacts with calcium iodide, it is going to switch out with the iodine rather than the calcium because the iodine also would carry a negative charge, similar to what chlorine would if it were bonded into a compound. So figuring out what displaces what is based off of the nature of the individual element that is by itself. If it's a metal, it will replace the metal. If it's positively charged, it will replace what's positively charged, and if it's negatively charged, it will replace what is negatively charged. The second to last type of chemical reaction we're going to look at is what is known as an exchange reaction. And this is a chemical reaction in which 2 substances exchange parts with one another to form 2 different substances. So essentially, these are going to be 2 compounds that exchange their negatively charged substances. The examples given on the right show just that. KBr and AgNO3 end up becoming KNO3 and AgBr. Again, those negatively charged ions are switching places. Notice that the polyatomic ions are not broken apart, they just switch spots. Na2SO4 and SrCl2 become NaCl and SrCO4. Again, we're trading places here when we look at our chemical reactions. So simply take what's negative, trade its places, and you know that you have an exchange reaction. The last type of reaction is very specific in the fact that a combustion reaction is a chemical reaction in which oxygen reacts with the hydrocarbon to form carbon dioxide and water. So even though the equations on the right aren't exactly what we're looking for here, the ones on the left are. You have some hydrocarbon, that is some compound that is formed from carbon and hydrogen. It reacts with oxygen and produces CO2 and H2O. So notice that the examples given on the left are very, very specific in terms of the chemical formulas and what types of products are produced. So it's very easy to recognize, provided you understand that a combustion reaction requires a hydrocarbon, requires oxygen, and produces carbon dioxide and water. So again, here we have our variety of different types of chemical reactions that we're looking at and the generalized formula for these. So I would make sure that you not only know these based off of what products are produced, but also get into the habit of understanding just the reactant side as well. Because eventually I'm just going to give you the reactant side, and it's going to be your job, based on the rules that we just discussed, to predict the products of those chemical reactions that are given. So now what I'd like you to do is take a moment, classify and balance the following reactions. We've got 4 of them here. Take a moment, go through them, and we will look at these here in just a moment. All right, so before we go through and balance these equations, we're just going to go through and determine their types, just like what we talked about. So we have 5 types we're going to discuss here. If I take a look at this very first one, we have a compound and a compound produces 2 compounds. It's apparent that whatever's negatively charged switch places as we look at the product side. So this is known as exchange. Here you have 2 things becoming 1, so that is going to be a combination. You have a carbon and hydrogen that reacts with oxygen to produce carbon dioxide and water, so this is combustion. An element plus a compound producing an element in a compound, this is displacement. All right, so now let's go through and balance these just like what we did before. So we've got 2 OHs on the left, I'm going to actually use a different color for this. 2 OHs on the left, 1 on the right, so 2 goes in front here. 2 sodiums now, 2 goes in front, and we're balanced. SO4 here is good. NH3, we're going to need a 2 here. And that balances everything out because we end up with 2 nitrogens, like what we have here. We need a total of 8 hydrogens. There's 6 here and 2 here. So that gives us a total of 8. For combustion reactions, balancing CHO is what you need to know. Carbon, hydrogen, then oxygen last. So start with carbon, 5 on the left, 1 on the right, 5 goes in front. 12 hydrogens, 6 goes in front. Now, make sure you add up the oxygens from both products of your chemical reaction. So you have a total of 10 here, and 6 is 16. So this needs to be an 8. So make sure you work through those very, very carefully. Here we got PB, we got H3PO4. I'm going to go through and do the hydrogens first. So we'll do a 2 here and a 3 here. Again, least common multiple of 2 and 3 is 6. That gives me 2 PO4s, which I'm good with here. We need 3 leads, so a 3 goes in front, and we're done. So again, make sure you can work to figure out what types of reactions you're looking at, and then work back and forth in order to figure out how to go through and appropriately balance them. We'll be back in just a minute.